What I would like to do in the next 15 minutes is to explain how it is possible to use nanophotonics and what we call optical metasurfaces for reducing the Étendue of an optical system and apply this, of course, for wireless communication. So this work has been done mainly by a postdoc in my group at the University of Eindhoven. And also I should, of course, acknowledge other co-workers at the TUE, but also at the Dutch Institute for Fundamental Energy Research, Mohamed Ramezan, Nix van Holf, and Quildefan. And this work was also done in collaboration with Facebook, in particular with Tobias Dicke and Thibault Peronel. And the results that I will be presented here has been already published in this publication. So this talk goes about reducing Étendue. So it's maybe good just to mention what is the conservation of Étendue in an optical system. So we have an optical system. So there is this fundamental quantity, which is the Étendue, which increases or at best can be conserved. So this Étendue is defined as the area of the source times the solid angle that is sustained at the entrance aperture of that source by this optical system. So this quantity, this product, increases by the optical system, or at best is conserved. And this Étendue, we already have seen that in this conference several times. So can pose a limitation. So set a limit for wireless optical systems, as if you have sources which have a large Étendue, so it's impossible to focus this down into a small photodetector, which limits then the bandwidth and the sensitivity. So here what we did in collaboration with Facebook is working this concept. So this is just an idea. It consists on basically using light conversion in order to reduce the Étendue. So here this is represented. So what we have is a source, a modulator source. It can be a laser of an LED. It can be moving and has a certain divergence. And then this is incident onto this optical system, which consists of this metasurface that I will explain in detail what are they. And it contains also a light emitting material. So you absorb this modulated laser light, and the emission of this light emitting material is in a well-defined direction. And then if you have this defined direction, you are reducing Étendue, so you can focus down into the small photodetector. So I will explain this in detail, how this works. But maybe I should also say that this is all based or inspired by Nanoantenna's phase arrays. So, well, we have an antenna phase array at radio frequencies. So this is an array of antennas, and we can scale down this concept into the nanoscale. So also to scale this at optical frequencies by using metallic nanoparticles. So this is an array of metallic nanoparticles that we fabricate here in Eindhoven, and then on top of this array of metallic nanoparticles, we can deposit a layer of emitters. So this concept of optical antennas, as I said, is borrowed from the radio antennas. So in a radio antenna, what we have is a current that is fit into a resonant element, the antenna. So this produces this current, and then is radiated into free space radiation. So this is the principle of an antenna. So if we scale this down to the nano scale, and then we have, instead of here providing a current through a coaxial cable, we put an emitter. So it can be a quantum dot, or it can be an emitting molecule. So this emitting dipole here can couple into this antenna, which then will radiate this light in a well-defined direction. So this concept was already introduced some years back. And now we're applying this not on a single antennas, but on an array of these nano antennas. So how does this work? I mean, I'm a physicist, so let me explain you also the physical process of these nano antennas, or these antenna phase arrays. So what we have here, in mind that we have here a plane wave that is incident onto this array of nano antennas. So this plane wave will then excite what are known as localized surface plasmon in these nanoparticles. So we have an electric field that drives these free charges in the metallic nanoparticle in a coherent oscillation, and this is what is known as a localized surface plasmon polariton. So these are characterized by, well, these are plasmonic modes, which are characterized by having high local fields, electromagnetic local fields close to the particles, but also by losses. So we have ohmic losses, which also, well, produce an absorption of this electromagnetic wave. Now we position these nanoparticles at the distance which is comparable to the wavelength of light. So then you can also have the diffraction. So we can have diffraction in the array of nanoparticles, and we can have the condition of Rayleigh anomaly. So this is the case at which, well, if we have a certain wavelength that is here incident and there is a certain angle here, the normal direction. So this Rayleigh anomaly will correspond to diffraction of this frequency or this wavelength into the plane of the array. Okay, so we have diffraction in the plane of the array. So this is a photonic mode, which is weakly confined to these nanoparticles. And now we can design this diffraction at a certain wavelength or frequency that is resonant with the frequency of this localized surface plasmon polaritons. And when we do that, so what we do is we couple these two resonances in that system, and we form this what we call collective plasmonic resonances, which are hybrids of these plasmonic and photonic modes of these localized plasmons and these Rayleigh anomalies, which share properties. So because there's an hybrid, so they share the properties, which means that we have high local fields, which are also weakly confined to the nanoparticles. And this turns to be very important because then we can couple emitters that are close to this metasurface or to this array of nanoparticles. And also because of this hybrid character, we have low losses in this system, optical losses, of course. So in extinction, so if we look at the optical extinction of one of these nanoparticles arrays, so what we see is something like this. So here we have a broad resonance. So this is a resonance that we can assign to the individual nanoparticles. And we have also diffraction at a certain wavelength. And as a result of the coupling of this diffraction with this broad resonance, we have this narrow resonance here, which are these collective plasmonic resonances. And well, here I explain all this by considering a plane wave that is incident on this onto this nanoparticle array, but we can also use reciprocity. So, which means that well, if we position now an emitter here close to this metasurface, so we will have a coupling of that emission into these modes of that system, and then they will be irradiated in the direction similar to the one as you will get these modes if you come well with a plane wave. So this is basically a reciprocity. So we can have a directional emission if we have also an enhanced extinction for a certain angle of incidence. So let's look now more into the emission, which is of course what is more relevant here. So here is an example. I will elaborate a bit more also in a few minutes. But here what we have is again one of these metasurface, this nanoantenna phase array, which is made of aluminum nanoparticles. And on top of this array, we deposit by spin coating a layer of 700 nanometers in thickness of polystyrene with dye molecules, so with light emitting molecules that can be excited at 450 nanometers. So this is a well extended wavelength in lighting applications, and these molecules emit at 620, or well, emit a broader spectrum, but we select here, and these emitters are at 620 nanometers. So here what uses are different emission profiles. So this is the polar image, polar plot image of the emission from different layers. So this corresponds to a layer of these dye molecules, a flat layer with all these nanoantennas. And when we have this layer on top of nanoantennas with different lattice constants, so here where we are just exchanging the separation between these particles, the nanoparticles, we see that this emission at 620 nanometers changes in direction, right? So of course, you know, this is a diffraction effect. So you change the lattice constants and you change also the direction of outcoupling of that emission of those molecules. And as you can see here for this particular lattices, so the emission is preferential in the normal direction, so perpendicular to the surface. So we can define now a photoluminescence directional enhancement, and this is basically the emission in a certain direction normalized by the emission of a reference, and the reference is just a layer with the molecules, but without the nanoantennas. So we define this enhancement, photoluminescence directional enhancement. We will have three possible contributions. So the first contribution is the change of the local density of optical states. So these molecules are in a well, photonic environment that will modify their decay rate. And this turns to be a small change to this directional enhancement that we see in the measurements. Another contribution is this directional outcoupling. So this is the most relevant for us. So this is basically outcoupling in certain directions, as we can see here in these images. And there is another contribution to this emission enhancement, which is the absorption enhancement. Okay, so we also have structures, nanostructures that can be resonant at this excitation wavelength. So this the 450 nanometers, and as a result of this this resonant excitation, you can also get an enhanced absorption and an enhanced emission. This is, however, for the applications of this Étendue reducer, something that we want to keep a constant, or at least constant, with respect to the to the angle of excitation. So what we want is to have an omnidirectional absorption for all possible angles, and get a very highly directional emission in a certain direction. Okay, so this is the working principle of this nanoantenna phase arrays. So let's also define now a figure of merit for this Étendue reduction, which is given by this expression. So here, this is simply an integral over the solid angle in a certain range of solid angles of the emitted power by this system of nanoantennas plus light emitting molecules, and normalized by the incident power. Okay, so if we have that this figure of merit is larger than 1, we have effectively a reduction of the Étendue of the optical system. And ideally, what we would like to have is this figure of merit as large as possible. So again, I will show now an example. This is the work that we did with Facebook, in which we have, again, an aluminum nanoparticle array. So here we keep the lattice constant, so the separation between the particles constant, 410 nanometers, in order to get emission in the normal direction. And we use a nanopyramids, so which has a base of 150 nanometers, a side base of 140 nanometers. The top size of the top facet is 80 nanometers, and the head is 150 nanometers. So again, we use the same molecules as before, as the example before. So these are this Lumoyen red in polystyrene. So we look to the absorptance spectrum. So this is on here. So we have this absorption, and then we have I will be showing measurements at 3 different wavelengths, excitation wavelengths. So we excite at 575 nanometers, but also at 533 and at 450. So we have, of course, a different absorption cross-section and different wavelengths, and we will see in a minute the effect. And this is just for completeness, the emission spectrum. So the measurements that I will be showing are at around 620. So this is the wavelength of detection. Okay, so this is the system. So the first thing is to characterize this layer of molecules and optimize basically the concentration of molecules in order to achieve the optimum performance. So here, what we have done is keeping fixed this thickness of the layer, of this polystyrene layer with the dye molecules, but without antennas. So this is just a thin layer of this light emitting material. So we investigated the absorptance and the quantum yield as a function of the concentration of molecules. Okay, so this is the concentration in weight percentage. And these are the 3 different wavelengths that I said that we were going to investigate this. So what we see is, of course, the first thing is that as we increase the concentration of molecules, the absorption increase. And the second thing that we see, and this is pretty logical, is that this absorption is larger when the absorption cross-section of the molecules is also higher, right? So we see the maximum absorptance at 575 nanometers. Now we can also look at the quantum yield, and the quantum yield, what it does, it decreases with the concentration. What we get here is concentration quenching. So we start packing these molecules closer to each other, so then they will start having a concentration quenching, which reduces this quantum yield. Now we can multiply these 2 quantities and define this figure of merit here, which is the same that I'm defining here, but integrated for all possible solid angles, right? So it's the integral over 4 pi. So this is defined by this product of the absorptance and quantum yield. Now what we can see here is that there is an optimum concentration of molecules at which this performance is the highest, and this is also for the case of having this excitation at 575 nanometers, so which corresponds also to the absorption of optimum of these molecules. So we get a concentration of about 8% and a wavelength of 575 excitation, so that are optimum for the performance of this system. Also, what we can see is that this quantities is smaller, much smaller than 1. So if we have this figure of merit equal to 1, so this will correspond to having a perfect absorption, so an absorption of 100% at the excitation wavelength, and a perfect emission, so a quantum yield of 1. Okay, so this is of course not the case here, and this is what this number is smaller than 1. So now the next thing is to look, as we did before, to see how this is the beaming of that emission. So when we just put these dye molecules, this optimized layer concentration of molecules on top of these nanoparticles. So this is what is shown here. So this is again the emission of the layer without the nanoparticles, without the nanoantenna phase array. And when we put these molecules on top of this nanoantenna phase array, we get again this beaming that I was showing before. So we get this beaming perpendicular to the surface, right? So in the normal direction. And here what we can also see is that this beaming can be different depending on whether we look on the front side or on the back side of the sample. And the reason for this is because we have these pyramids. So these pyramids, basically what they are doing is breaking the symmetry of that system, so which basically enhance the light outcoupling in a certain site, in a certain direction. In this case, is this back direction. So we can then position the sample in front of a detector. So this is what is done here. So the sample is located like this, and then we have the detector looking at the back side, so at the substrate, because we get the maximum emission. So we excite here then a certain angle, and then we can measure the emitted intensity. So this is the photoluminescence, the emission, and we can basically control this angle of emission that we are detecting with the diaphragm. Okay, so we put here a power meter, a lens, but we control basically the light outcoupling angle that we measure by placing here a diaphragm. And then we can change basically the size of this diaphragm in order to retrieve this outcoupled power, normalized by the input power, so the excitation power, and as a function of the size of this diaphragm, so as a function of the solid angle that we are basically measuring. And we see here again the performance of the layer of the dye molecules without the nanoantennas. And when we put these nanoantennas on top, so we see that there is an enhanced emission in the forward direction, in the normal direction. That's of course what you can see here in these images. Okay, we can again define this photoluminescence directional enhancement that I was introducing a couple of slides before, and then what you can see is basically divide this measurement by that. One is that we are enhancing basically this directional outcoupling at this emission by roughly a factor 3.5. Is we increase the solid angle of detection, so this start reducing, and of course if we make it very large, so this will reduce more. But anyway, we're interested in having this beam emission at very small angles. So then as a thing that I want to show is, what is this figure of merit, as I was defining that before. And then this is now defined in a small solid angle. So this is the solid angle of these measurements for an optimized wavelength of excitation. So the wavelength of maximum absorption of these molecules, 575 nanometers. And here this is shown as a function of the angle of excitation, right? So what we are changing now is this angle here, this angle of excitation. And by doing that, so we retrieve this figure of merit for this solid angle in 4 different situations. So what we have here is the low figure of merit measurements corresponds to the layer of dye measured from the front or for the back side, from the substrate or for the air side of the sample. So without antennas, so these are these measurements here. And when we just position these dye molecules on top of this antenna phase array, we have an enhanced figure of merit. And the most interesting one, of course, is the one that gives the highest figure of merit, which, is not yet bigger than 1. So for certain angles approaches 1, so Étendue reduction. But what is more important here is that this is fairly constant, so it's not changing with the angle of excitation. So here the next thing, of course, is to increase these values above 1 in order to effectively reduce the Étendue. So how this is can be done. So this is now summarized in my conclusion. So this can be done by basically enhancing in the absorption cross section of this system of these molecules. So we've been using molecules at a very low concentration to avoid concentration quenching, which also have a very limited absorption. So this is something that could be improved. So by, for instance, using quantum dots, which have a much higher cross-section, absorption cross-section. And of course, another thing that can be improved is the quantum yield or the quantum efficiency. So this is also something that can be done by controlling basically the emitters. In any case, what these measurements show is that it's possible to reduce, in principle, this Étendue using optical nanoantennas and antenna phase arrays. And here, what we have shown as well is that we can achieve a sphere of merit of approximately 1 over a wide range of angles of excitation. And again, just to stress that this sphere of merit of 1 will correspond of having a perfect emission in a system that absorbs 100% of the excitation wavelength, which is by far not the case of the dye molecules alone without the nanoantenna rays. So with that, I'm almost finished. So if I still have something like 30 seconds, so I would like to highlight this extract. So this is taken from the most famous lecture of Richard Feynman, in which most of the work on nanotechnology can be reflected even these days. And here I would like to read this, which is just taken from that lecture, so of 1959. So here what Feynman said is that, well, consider, for example, a piece of material in which we make little coils and condensers, which are well defined in the circuit. So that will be corresponding basically to the molecules that we are using in our samples. And then with little antennas. So these are the nanoparticles that we are having. So sticking out at the other end, a whole series of circuits. And it is possible, for example, to emit light from a whole set of antennas, like we emit radio waves from an organized set of antennas to bring the radio programs to Europe. So he was asking that. And he was saying here the same things will be to bring light out in a defined direction or in the definite direction with a very high intensity. And this is actually what we are doing. Not from Europe to the USA, but well, just from an optical system into a detector. And here also Richard was finishing this paragraph saying that between brackets, perhaps such a beam is not very useful technically or economically. So we're also trying to do is to show that at least in this part he was wrong. And with that, I would like to finish my presentation.